One of the tools that you should always have in your network toolbox is a network protocol analyzer. And this comes in a lot of different forms. It could be a physical device that you plug a network cable into, or it might be a wireless device that you use in proximity to a wireless network, or it could be software that you install on a mobile phone or on a laptop or a desktop or a server. Many different forms that we have for network protocol analyzers, but they all do the same thing. They capture network traffic. Now, as you might imagine, the placement of the protocol analyzer is important in order to capture the traffic that you're interested in. So for example, if you want to capture traffic going out to the internet, your best bet is to have a network protocol analyzer, otherwise called a packet sniffer, at the point between traffic from your internal network getting to the router, getting out to the internet. So placement is a big deal. So we know then that we can have a hardware device or software as our protocol analyzer tool. We know that network placement is important. Now, what we can also do is actually plug, for example, a laptop computer into a specific switch port. Now, it doesn't have to be directly in the switch port in the communications room. It might be through the wall, but in the end, what we can do is configure that switch port in something called SPAN mode, Switched Port Analyzer mode. All that means is all of the traffic for all of the switch ports is going to be copied to that one where you're running your network protocol analyzer. So you get to see everything in that network switch. Normally you don't. The default behavior for a network switch when you're plugged into a port is you only see your own traffic or who you're communicating with. Of course, you'll see broadcasts and multicasts, but you're not going to see private conversations happening between two other devices on the switch. Not by default, you're not. So if you're going to capture network traffic using software like Wireshark on a device plugged into a switch, you need to make sure you talk to the switch administrator to make sure that your switch port is seeing all of the traffic. Otherwise, it's not a true picture of what's happening on the network. So you can use most common tools that are used for network packet capturing to capture traffic on a wireless network, like a Wi-Fi network, or to capture Bluetooth wireless traffic, and of course to capture traffic on a wired network that you're actually physically plugged into. The great thing is that you can save packet captures for later analysis, just like you can using tools like the ZenMap front-end GUI tool for Nmap. You can save network scans and review them later. Here, we can save packet captures and review them later. You know what else you might want to do? You might want to take a packet capture where you might suspect there's something suspicious going on in that traffic. There are online services that are free where you can upload your packet capture file and it will analyze it for you, telling you if there's anything weird or suspicious, like maybe some malware that's trying to talk back to a command and control server somewhere else in the world. So the other thing to remember is don't believe everything you see. And what I mean by that is when you capture network traffic, take it with a grain of salt. That traffic could easily have been forged. There's a free tool that's called HPing. And what this lets you do is it lets you create network traffic. You can literally spoof everything about a packet, every header in a packet, even the payload or the data. So you could make it look like any type of traffic is occurring on the network that you choose, even nefarious bad stuff, and you can make it look like it's coming from any IP address you want it to. So that's what I mean. Take it with a grain of salt. Now that's why we need to make sure we limit or restrict who gets on the network in the first place. You can also filter network traffic either when you're capturing it or after you've captured it all. You can have a display filter. For example, I've captured a lot of network traffic over time, and what I want to do is I want to filter it and only look at HTTP traffic, for instance. So we can do that too. So we have capture and display filters. We have the ability in our protocol analyzer to view packet headers. When we say packet headers, all we're talking about is the addressing information. It's kind of like a physical letter that you would send through the postal service, snail mail as we call it. When you look at the front of the letter, you have all the addressing information. That's like packet headers. That's all that's in it. But if you actually open that letter, that's like looking at the payload in a packet, the data. And so you can see all of that when you capture network traffic. The only exception being if that network traffic is encrypted and you don't have a decryption key with your network protocol analyzer. Well, then it's going to look like it's all scrambled symbols. You're not going to make sense of it. We can also analyze TCP streams to view an entire conversation thread, so to speak, that uses the TCP transport protocol. Now, Wireshark is a free open source tool that we can run on many different platforms, and it gives us a GUI. There's also a command line component. But in Linux, what's built in and has been for a very long time is a protocol capturing tool called TCP dump. Also, the Cisco NetFlow protocol allows you to capture IP traffic at the network infrastructure level, such as on a router. So you have the ability to capture it at that point on the network. So there's also an SFlow standard, and the Cisco NetFlow standard is similar to that. These are just standards that allow you to capture network traffic on an infrastructure device on the network. So the SFlow standard is similar to NetFlow, but it's superseded by something called the IPFix standard. So at this point, let's take a look at a screenshot from Wireshark. Here in Wireshark, a packet capture has taken place, and at the top in the frame where the packets are colored green, we have just basic information. We can see the source and destination IP address, the higher level protocol like HTTP, and in the middle of the screen, we have the packet headers. Remember, that's just the addressing information to get the packet from point A to point B. So what's opened up in that example is the Internet Protocol, or the IP header. We can see it's version 4. This is an IPv4 packet, it's not IPv6. And then we see the fields within that header. Things like the total length in bytes, the time to live, the TTL. The TTL in the IP header is decremented normally by a value of 1 every time that packet traverses a router. In some cases, some routers might decrement the TTL by 2. But this is one way to get a sense of how far the packet has traveled. If an operating system starts the TTL at 128 and you capture it and the TTL is still 128, it hasn't left the local area network. Although it might be a forged packet. That could be forged. Like I said, take it with a grain of salt. Also in the IP header down below, we can see the source and destination IP addresses with following headers like the TCP header and the HTTP header. And finally, we have the payload or the data in the packet at the very bottom. Now again, if this is encrypted traffic, then you won't be able to make sense of it. But if we have clear text transmissions, like we've been talking about, this is where you'll be able to see it. So be aware that we've got a number of different ways that we can capture and analyze network traffic.